Welcome to another session of our math tutorials. In our previous video, we looked at the mutually exclusive event. Today, we will be looking at the independence event and the general addition rule. When events are mutually exclusive, the general or the special addition rule can be applied. But however, it is not all cases that you will encounter mutually exclusive. So the general addition rule is given as the probability of A plus the probability of B minus the probability of A intersection B. So this is the general addition rule. This is the general addition rule. So let's consider this particular example on board. Given that probability of X is 0.58 and probability of Y is 0.4, if the probability that both occurring is 0.25, what is the probability that either X occur or Y occur? We were made to understand in the previous video that improbability or indicates addition. Or if you want to know that this particular example, the example that we are about to solve is under mutually exclusive, you have to consider three phrases. That's or, either, and union. So if you see or, either, or union in any question, you have to remember that it is under mutually exclusive event. But in some instances, you can apply the general addition rule in the mutually exclusive events. So I have this example that I want to cite so that you understand the general addition rule or the mutually exclusive events better. You see, when you go to a bank, you can have a customer who is having a savings account or let's say a current account, or the person might have both accounts. So you can see that the person, let's say a customer A, let's say a customer is having a savings account. That the customer is having a savings account and at the same time is having a current account. Or the person is having both savings accounts and current accounts. So you can have one customer who is having a savings account as a separate account on its own, and the person is also having a current account as a separate account. Or we have one person or a customer who is having both savings account and current account. So this is a typical example of the general addition rule under the mutually exclusive event. So this example relates to the example that is on the board. That's what we are about to solve. So given that a probability of X is 0.5 and the probability of Y is 0.4, if the probability that both occurring, that's both the person having both savings account and current account at the same time is what? Is 0.25. What is the probability that it's either X or what? Y. So what is the probability that the person is having a savings account or a current what? Account? So we are going to use this particular formula on board to solve this question. So we are given the probability of X, which is what? So our solution, we have probability of X equals 0.58 and probability of Y to be what? To be 0.4, and probability of both occurring at the same time, that's the person having, let's say, a savings account and a current account at the same time, is that's probability of both occurring. What is the probability? If the probability that both occurring and the probability of having X and what? Y is equal to what? 0.25. Find the probability that the person is either having X or what? Or Y. Remember, in probability, when you hear of or, it means addition. So we are going to have the probability of X or the probability of what? Of Y minus the probability of the intersection, that's the one belonging to X and at the same time what? Belonging to what? To Y. So we are going to have probability of X intersection what? Intersection Y. X intersection Y. So we are going to have 0.58 plus 0.4 minus 0.25. So the probability of having X or Y is given us, or we have 0.58 plus the 0.4 minus 0.25, which gives us 0.73. 0.73. So this is an example under the general addition rule. Example under the general addition rule. So I take the question again. Given that the probability of X is 0.58 and the probability of Y is 0.4, if the probability that both occurring at the same time is 0.25, what is the probability that either X occur or Y occur? You remember the example that I cited. You can have a customer who is operating a savings account or a current account or a savings account and a current account. So the probability that the person is having, let's say, a savings account is X, current account is Y, and you have to find the probability that the person is either having a savings account and a current account, that's both accounts at the same time, is what, 0.25. Both accounts at the same time is 0.5. So let's find the probability that it's either what, savings account or what, a current account. So we have the probability of both events occurring, which is end, indicating what at the multiplication is what, X and Y is 0.25, and the probability of X is what, 0.58, probability of Y is what, 0.4. So we are going to add the two minus the probability of what, both occurring, which is 0.25. As simple as that. Now let's look at the independent event. I have an example that I wanted to solve under the independent event. Independent events. What man called? Hey, who the cutting? Man calls him the cutting. Under independent events, the occurrence of event A does not affect the occurrence of event B. So assuming you have a die, let's say you have two die, that's a six-sided die. Let's say you have die 1 and die 2. And you throw this particular die 1, that's both die 1 and die 2. What is the probability that the first one is an even number? You get an even number, and the second one is what? It's an odd number. So this is an independent event. So basically, if you can get an even number in the throw of the first die, you can also get an odd number in the throw of the second die. But in the case of, let's say, one die, let's say you have only one die, you have only die 1, you cannot get both even number and odd number at the same time, because the die has only 6 numbers, which is 1 up to what? Up to 6. 1 up to 6. And 1, 3, 5, they are odd numbers. We have 2, 4, 6 as what? As even numbers. So when you throw a die, it's either you get what? An odd number or what? Or an even number. That's in the case of one die. But in the case of you throw two die, or let's say even one die and you throw it twice, you can get the first one as what? As even number, and the second one as what? As odd number. That's under independent events. The occurrence of event 1 does not affect the occurrence of what? Of event 2 or event B. So let's look at the example on board. The probability that a man will be alive in 30 years is 0.6, and the probability that the wife will be alive in 30 years' time is 0.7. What is the probability that both will be alive in 30 years' time? So the question says that the probability that a man will be alive in 30 years' time is what? Is 0.6. And the wife will be alive in 30 years' time is what? Is 0.7. So we let the man, which will be alive in 30 years' time, be what? Be M. And the wife, which will be alive in 30 years' time, be what? Will be W. So the probability that the man will be alive in 30 years' time is what? Is 0.6. And the probability that the wife will be alive in 30 years' time is what? Is 0.7. Now the question says that what is the probability that both will be alive in 30 years' time? The probability that the man will be alive in 30 years' time doesn't depend on the probability that the wife will be alive in 30 years' time. They are both independent. They stand on their own. It could be that the man will be alive in 30 years' time, but the wife will not be alive in 30 years' time. Or the wife will be alive in 30 years' time, and the man will be not alive in what? In 30 years' time. So they are both what? Independent. They stand on their own. One does not depend on what? On the other. So the question says we should find the probability that both will be alive in 30 years' time. If both will be alive in 30 years' time, basically we are going to have the probability that the man will be alive and the probability that the wife will also be alive, because they are not what? They are not dependent. They are independent. It could be that the man will be alive and the what? And the wife will also be alive. That both will be alive in 30 years' time. If it was to be all, that one, it will have been an what? Dependent event, because you can have the wife being alive and or the what? The man being alive. But here is the case, they are both alive. So it becomes what? An independent event. The man being alive doesn't depend on the wife being alive. And the wife being alive doesn't depend on the man being what? Alive or dead. So we are going to have the probability of the man being alive as well, 0.6. And the probability of the wife being alive is what? 0.7, which gives us 0.6 times 0.7 as 0.42. So the probability that both the wife and the husband being alive is what? Is 0.2. Now let's look at the second scenario. What is the probability that both will not be alive in 30 years' time? This is where the challenging comes from. In the question, we are giving the probability of the man being alive and the wife being alive, but we are not giving the probability that the man will not be alive and the wife will not be alive. In complements and the probability, when you want the probability that, let's say, the man will not be alive in 30 years' time, it is 1 minus the probability of what? The man not being alive, which is what? Which is 0.6. So if its formula is given us the probability of the man not being alive, let's represent it by m bar, the probability that the man will not be alive. So the probability that the man will not be alive is m bar is equal to 1, which is certain, minus the probability of what? Be alive, which is what? 0.6, which gives us what? 1 minus 0.6, which is 0.4. So the probability that the man will not be alive in 30 years' time is what? Is 0.4. Let's look at the wife too. The probability that the wife will not be alive, which is the W bar, is what? Is 0.7 equals 1 minus 0.7, which is 0.3. So the probability that the woman or the wife will not be alive in 30 years' time is what? Is 0.3. But the question doesn't demand us to find they not being alive. It says that if you find the probability that both will not be alive in 30 years' time. Now that you know that the probability that the man will not be alive in 30 years' time is 0.4, and the probability that the woman will not be alive in 30 years' time is 0.3, we can go ahead and find the probability that both the two will not be alive in 30 years' time. And it is given as the probability that the man will not be alive and the probability that the woman or the wife will not be alive, which is given as 0.4 times 0.3. 0.4 times 0.3, which equals to 0.12. 0.12 is the same as 3 out of 25. 3 out of 25. So the question says probability that both will not be alive in 30 years' time. So if both will not be alive, remember we were given the probability that both will be alive as what? Will be alive at, let's say, 0.42. 0.42. That's if you find the probability that both will be alive in 30 years' time is what? Is 0.42. And the probability that only the man will be alive is what? Is 0.6. And the probability that the wife will be alive in the probability that both will not be alive in 30 years' time is the probability that the man will not be alive times the probability that the wife will not be alive, which gives us 0.12. In our next video, we are going to look at conditional probability. For now, thank you. See you in another video.